Hi. In this video, we are going to be continuing with simple harmonic motion. Last time what we ended up discussing was that the net force that acts on a spring or on a mass spring system is negative kx, and that's Hooke's law, right? So if you take a mass spring system over here, and then you attach it with a mass m, as we can see, then the net force that's acting on this mass spring system is negative kx. And what we're saying is that this mass spring system will be moving to the left and to the right and so on. Okay? So based on that, we were able to get that the mass times the acceleration in the x direction. So this is the set of axes that we're going to be using. So the mass times the acceleration in the x direction is equal to negative kx. And so therefore, mass times acceleration in the x direction plus kx is equal to 0. Okay? And what we said was that by using a notation of differentiation, we can say that m times d square x by dt square plus kx is equal to 0. Okay? So this becomes a differential equation, right? And the reason it's a differential equation is because you only have one unknown variable, which is x, and you're expressing it as a form of its derivative to make an equation. Okay? Now, you don't need to know how to solve these equations. Basically, you just need to know the result that comes out of it, and that is that the acceleration is negative omega squared x. Okay? Now, we also saw over here that because the mass times acceleration is plus kx is 0, then this states that the acceleration in the x direction is negative kx divided by m, which is negative k by m times x. And you see over here that this omega squared and k by m become equal. So omega squared is k by m, so therefore omega is the square root of k by m. Okay? That's the important thing that you can see over here, right? Now, I think this is very important that you understand how we get the sine and cosine curves. So we said one of the things in simple harmonic motion is that your displacement, your velocity, and your acceleration are functions of sine or cosine, right? So they're functions of sine or cosine. Okay, so let's just put a mass spring system over here. Let's say if I attach a mass m to a ceiling, and let's say that this is my equilibrium position, so this is equilibria. Then now let's say we make this displacement time graph. So this is displacement and then this is time. Okay, so in this case what we can see is that this pendulum this mass spring system, we'll also make this we can also say that at this point you have your let's try it this way. I think this would be a better way. So let's say you have a mass spring system on the ground, you're attaching it to a spring, and this spring is in your equilibrium. Okay, and let's say we bring this a little bit downwards, so it comes over here. Okay, so because the equilibrium position is the same as here, this is the starting point. Okay, now after this, what's going to happen is that the spring is going to extend and you're going to get this extension. So this is going to be the max amplitude, right? Because this over here becomes the amplitude or the maximum displacement from the main position. And then similarly, let's say that this is when the mass is at its lowest point. Okay, this is when you have the maximum compression. Then if you draw this, then this sort of becomes your minima. Okay, so in this case what we see is that this mass m over here, it starts off at 0, which is here, then it goes high, then it goes low, then it goes back to equilibrium position. Okay, so it goes high, then it goes low, then it goes back to equilibrium. Okay, it goes up, equilibrium, goes down, equilibrium, right? So if we write it in terms of your displacement time graph, and what you can see is it goes up and then it goes down. Okay? So this is what we get over here, right? In this case, it goes up, it reaches its max height or the max amplitude, it goes down. So in this case, when it goes to the max height and goes down, that's what it's doing. Then it goes to the minima, then it goes back to 0. And so as you can see that because the initial displacement and the final displacement are the same, so this is one period, okay? This is one complete oscillation that we can see, okay? So this is similar to a sine curve, right? So what you would be seeing for a sine curve is that we start with this as our original position. Okay, we start the equilibrium to be our original position. But now, let's say that if we start off by looking at if we start off by seeing a cosine curve, for example. Okay, so let's say that instead, let's make this to be our starting position. Okay, so we start off at our maximum displacement. This is our starting position. Then we go to our minimum position and we go back. So that's one oscillation. So the starting point, then it goes to the minima, then it goes back. So it's back at its original position. That's the oscillation, right? So it goes all the way down, all the way up, down, up, and that is one oscillation. Okay? So if we look at that, then, what we would essentially be seeing over here, right, is that with time, this is falling down, okay? So this is falling down with time, like this. And then it's going back up, okay? So you get this sort of V shape. So it's falling down, it's going up, and then it's going up, okay? So in this case, what we have seen is that this curve looks like a sine curve, and this curve looks like a cosine curve, okay? So when you solve the differential equation, you would get x in terms of either a cosine curve. It can either be a cosine curve or it can be a sine curve. So this just depends on your starting point, okay? So what starting reference you're using, that's the only thing. And then if the displacement is a function of either sine or cosine, so this is HL stuff, like this one over here, you don't need to know it in SL, but this will be x naught cosine of omega naught t, or x naught sine of omega naught t, where t is the time variable, and then omega is your angular velocity, it's delta theta by delta t, and then over here x naught is your amplitude. So you don't really need to know that, I would say. It's more of like if your displacement as a function of time is of sine or cosine, then the velocity will also be a function of sine or cosine, and then so will your acceleration. Acceleration will also be a function of sine or cosine. Okay? So that's the main idea, the main intuition you take for why the displacement and velocity are functions of sine and cosine, right? And then last time we looked at this graph over here. So you need to know that for simple harmonic motion, the defining conditions are that the acceleration is proportional to negative x and the acceleration is proportional to omega square. So this is some form of theta. So you always get this equation that acceleration is negative omega squared x. Okay? Now, when you get this system, we ended up seeing last time, right, is that let's say that if this is your, if this becomes your displacement in the x direction, this is negative x, this is a, and this is negative a, then you get this line over here. Okay? Now this line just becomes the acceleration is negative omega squared x. Okay? So if you take this negative omega squared and you graph it, where acceleration is proportional to negative x, you get this following graph. So in this case, when the displacement is in the negative x direction, the acceleration is extremely positive. when the displacement is in the positive x direction, the acceleration is extremely negative. Okay? Now, what this ends up essentially meaning, right, is that when we graph this equation, a is negative omega squared x, then omega is just a constant. Okay? So, let's say if you have an equation y is negative kx and k is just a constant, this is a similar equation. And what we have seen is that we know that for a linear equation, y is mx plus c, where c is the y-intercept. So over here, the y-intercept is, going to be 0, 0. So we don't really care much about the y-intercept. But this is an equation of the form y is m times x. So if we have acceleration is negative omega squared x, then in this case, this negative omega squared is a gradient. Okay? So this ends up becoming a gradient, and sometimes what they can do is that they can give you this graph in exams. Okay? And so if they give you this graph in exams, then the way you can look about it is that you can simply find the gradient. Okay? So the gradient, they'll give you some points of acceleration and displacement. So you can just say that the gradient in this case is y2 minus y1 by x2 minus x1. And what you will see is that because the acceleration is negative omega squared x, then the gradient of this graph becomes negative omega squared. Okay? That's what the gradient of this graph ends up becoming, right? Now, the other thing we can do is that we can look at the period and we can get a formula for the period, okay? So the way we would go about it over here is that we know that the period t, so we know that in this case our angular velocity omega is 2 pi by t, which is the period, and we know that the time period is 2 pi by omega. Okay, and we also saw in the last lecture that the acceleration is negative k by m times x, and we also ended up seeing that the acceleration is negative omega squared x. Okay, so the reason we get this equation is because mass times acceleration is negative kx, that is Hooke's law, so acceleration is negative km times x, and this equation just comes from the fact that mass times acceleration is negative km times x, and then you can make a differential equation where m times d square x by dt square plus kx is equal to 0, and then if you solve it, you get this equation in that form. Okay? Now, when you get both of these equations, you can clearly see over here that omega squared is equal to k over m, so therefore you can see that omega is the square root of k over m. So we just substitute it over here. So the time period is 2 pi by omega, which in this case is just 2 pi divided by 1 divided by omega, which is 2 pi by 1 divided by the square root of k by m. Okay, which, this becomes 2 pi by 1 times root k by root m. So that's just simple math. And then this becomes 2 pi. So you take this up and then you take this here. So 2 pi times root m by root k, which is 2 pi square root of m by k. Okay? This is your time period of the oscillation. All right? So in this case, when they give you omega, sometimes, and then like if they give you the mass and the spring constant, then you can calculate the time period of the motion. Okay, and this is where the previous example comes into place, because they can give you this acceleration displacement graph, and then based on that they can tell you to find the time period, right? So the way you would go about it is that you would simply find omega. So we know that the acceleration is negative omega squared x. So the gradient of this graph, m, is just negative omega squared. So once you find negative omega squared, then you can just say that the time period is 2 pi by omega, and then you can solve for the time period. Okay? So that's the basic idea that we end up seeing over here, right? So in this case, the main thing is the displacement x is a function of sine or cosine. It just depends on the starting position. In a mass spring system, if you start from the equilibrium and then you graph it, then the mass goes higher, it goes to its extension, then it goes lower, when the lowest position over here, and then it goes back. So this shows a sine curve, okay? And then on the other hand, for a mass spring system, if suppose you show this to be your starting position, so this is at its max height or the maximum displacement, then you start at your max height, you go to your min height, and then you go back, and then this resembles a cosine curve. Okay? You don't really need to know much about these. That's more of an actual concept, but you need to know that they're sine and cosine functions of time. Okay? So that's the basic idea about it. And then the last thing we can also look at is frequency, right? So we know that frequency is 1 by time period, and we know that the time period, right, is just 2 pi square root of m by k. So sometimes they can ask you to find the frequency of this curve as well. Okay? Now, so that would be the main idea about it. Okay? All right. So that's good. Now, after this, what we can also do is that we can we can just look at these sort of systems, right? Now, so in summary, for simple harmonic motion, if you have got acceleration, and then if you have got displacement, then the defining condition is acceleration is negative omega squared x, and you get this sort of graph over here. And the gradient of this graph m is just negative omega squared. Okay? And just remember that they're sine and cosine functions of time in a mass spring system as the mass goes up and down. So if I have a mass spring system, and if the mass is going up and down, if you add a time variable, you would get this sort of curved function. So this would be your displacement, this would be your time, and then you're getting a curved function depending on where you start, right? So this would be the sine, this would be cosine, and that's how you would end up going about it. Now, in the next part, which is part 5, so in part 5, we are going to be focusing on energy in simple harmonic motion. So that's a fairly quick part, okay? And see you then.